A total eclipse of the Sun was predicted to occur on August 21, 2017. The NASA Space Grant Program had been working with over 50 organizations across the United States to launch high-altitude research balloons in order to stream live video and conduct experiments at heights above 60,000 feet. Arizona Near Space Research, or ANSR, is an amateur radio club that specializes in launching, tracking, and recovering these high-altitude balloons. They traveled to Glendale, Wyoming to support the flights of 2 balloons carrying payloads built by students from Embry-Riddle University in Prescott, Arizona, and by Arizona State University in Tempe, Arizona. In addition, there was a 3rd payload built by the University of Central Arkansas, which was mailed to ANSR to be flown out on one of the balloons. The ANSR members started to arrive on Friday, August 18th. They spent the day on Saturday scouting for a suitable launch site, which, accounting for the upper-level winds, would place the balloons approximately 10 miles south of the park, at an elevation of 60,000 feet or more, precisely at the time of eclipse totality. On Sunday, it was time to begin setting up and testing the ground station that is used to point the highly directive dish antenna at the balloons for the best chance of getting a strong signal on the downlink. We began by setting the rotator mount on a somewhat level piece of ground. It was difficult to find such a place, but an assortment of rocks was used to level out the legs, making the platform steady. Next, a vertical mast was placed in the mount to get the antennas off the ground high enough to avoid any injuries to the eyes. The azimuth elevation rotors were placed on top of the vertical mast. This is a set of servo motors which are capable of turning in a 360-degree circle and elevating the antenna from 0 degrees to 90 degrees in elevation. This allows the system to point precisely at any point in the sky. We had a difficult time getting the stand to be stable on the uneven, rocky soil. We tried digging around the legs of the stand, used sticks underneath the stabilizing cross legs, but it wasn't being easy on us. Finally, we found some relatively flat rocks to place under the cross legs, and by sliding them along the legs, we were able to get the stand level in both horizontal axes. Later in the day, the wind picked up considerably, so we ended up tying some rope from the top of the vertical mast to the ground and secured them with tent stakes. We didn't want the wind to blow the array over, possibly damaging the microwave dish. Finally, we bolted the rotors to the mast to secure them in place while we finished the construction. Through the elevation rotor, a horizontal mast is secured using 2 large U-bolts. This mast will hold 2 antennas. The dish is fairly heavy, so we use a steel pipe for this horizontal mast. Next, we assembled the 5-element 2-meter beam. This is used to receive the 2-meter APRS beacon from the balloons. The antenna is made by Comet, and it's really nice to put together on site. It comes folded up with the elements secured by thumb screws. We simply loosen all of the thumb screws, rotate the elements to their vertical positions, slide them into their plastic clips until they are centered on the boom, and then tighten the elements down by hand. Then we take the driven element, remove the thumb screw from its mount, place the element in the correct pre-drilled holes on the boom, and insert the final thumb screw to tighten it down. The beam is then mounted onto the horizontal mast using the attached mast clamp. The coax is attached to the antenna and adjusted to leave a drip loop hanging down. This gives the coax enough slack so that it does not get in a bind while we rotate the antenna array. It's important to align the array to true north. Typically we use an app on our cell phone to find true north and double check with the team constructing the student's second antenna array. We had some confusion here because the two arrays were pointed in different directions. After double checking, we found that the student array had not yet been calibrated to north. After running through their calibration, both arrays were pointing in the same direction. One final tweak and we were able to tighten the rotators to the mast, fixing their true north position. Next, it was time to mount the 2.3 GHz dish to the mast. This is usually a two-man job, one person holding the dish in place and a second person tightening the mounting hardware. You want to get the dish as close to the center of the mast as you can, as it's quite a bit heavier than the small 2-meter Yagi on the other end. That way it's not tending to tip the mast to one side. We use a small bubble level on the mount of the dish to confirm that it's level. It's important to start in a 0 degrees elevation position. If this is off, the signal will not be strong enough to provide good data. It's also a little tricky in that there's some play in the bearings of the rotor. So you have to tighten the clamp such that when you stop holding it up with your hand, it comes to rest in the correct position. Here, a student is mounting the modem to the back of the dish. There's a slide-in snap-lock mount for the modem. Once it's mounted, a Cat5 cable is run from the modem to the student's laptop computer that receives the data. At this point, we are inside the tent, connecting the rotor cables, radio coax cable, and data cables to the tracking station controller. 2-meter antenna coax attaches to a receiver, which provides audio APRS signals to a packet radio modem. The packet radio modem then decodes the APRS packets and provides an RS-232 data stream output. This feeds an RS-232 to USB converter, which in turn plugs into the ground station laptop. There's a custom program written in C# by a club member, K7GGG, Gary of Payson, Arizona. This program receives the balloon position reports in APRS format, pulls out the relative data, which is latitude, longitude, and elevation of the balloon. When the program is started for the first time on site, we manually enter the ground station's coordinates. Having these two sets of data, the program can then calculate the correct azimuth and elevation to point the antenna array at the balloon. It sends out a serial data stream to the antenna controller, giving it a bearing and elevation needed to complete its task. The rotor controller then commands the rotor to turn in the correct direction toward the target bearing and elevation. It reads the current bearing and elevation at the same time, comparing it to the target. When the position read from the rotor matches the target position, a command is sent to stop the movement. Once we're all hooked up and have our programs running, it's time to test the range of motion for the antenna array. We want to make sure there are no cables binding or other hardware binding on the array when moving to the extreme ends of its ranges. We discovered a problem here in that the modem on the back of the dish was binding against the rotor. when rotated to its extreme upright position. The student corrected this by removing the modem from its mount and remounting it in a slightly different position such that it was no longer binding. At this point, we decided we really needed to be in a position to watch the antenna array while it was in operation. It would not be good for something to get hung up and break in the middle of the mission. So we disconnected everything from the tracking array station in the tent and brought the equipment outside to be set up on a table next to the tent. This would require a cover if we had some rain, but that was not likely. While we watch the setup outside, let me continue explaining the computer setup. In addition to the custom program for moving the antenna array, we also have a commercial mapping program called APRS-IS32. This program plots the position of the balloons on a map to give us a graphical reference of where they are at. It also provides a log data of the balloon positions that can be parsed later to analyze it if needed. This program is fed from the same receiver that feeds the K7GGG program. But in this case, instead of going through a packet modem, the audio from the receiver is fed directly to the microphone input of the laptop. Then a program in the laptop decodes the audio and provides the APRS data to the mapping program. So we actually have two programs decoding APRS, one of them inside a APRS modem, and the other one is just a software program in the laptop. One final range of motion test and a small adjustment of a cable to prevent binding, and we are ready to go for our flight the next morning.